let's think about neuronal communication and specifically how the resting potential is maintained across the axon membrane of a neuron. Now, this would be a 3-mark question, possibly a 2-mark question. Let's just remind ourselves what resting potential is. We say that a neuron is at rest if it is not transmitting an electrical impulse. So it's not firing an action potential, it's just at rest. The membrane is at resting potential, which is about minus 70 millivolts. It does vary slightly from neuron to neuron, but resting potential is about minus 70 millivolts. Okay, we're going to use this diagram to help us answer the question. So how is the resting potential maintained? First thing to mention is you've got sodium ions going out. So from the inside of the axon, they're being moved out across the membrane. And at the same time, you've got potassium ions being moved in. Now, the name of the protein that does this, it's called the sodium-potassium pump. Okay? So the sodium-potassium pump is moving sodium ions out of the neuron or out of the axon, and at the same time it's moving potassium ions in. However, to get the mark, make sure that you use the word pump or that you say this is active transport, because this protein requires ATP to do this. So it's actively transporting sodium ions out and potassium ions in. Okay, so marking point 1. Sodium ions are pumped out of the axon and potassium ions are pumped or actively transported into the axon. It's really important that you remember they're ions. A lot of students will just say sodium moves out and potassium moves in, and that is not correct. These are ions, so you can use the symbol if you want, or you can remember to put the word ion after sodium. If you do know numbers, you can include those numbers. You don't have to get the mark, but it actually moves 3 sodium ions out for every 2 potassium ions that it moves in. The way I remember this, by the way, is I just remember SOPI, sodium out, potassium in, SOPI. It's a nice way to remember it. Okay, so you can have that one. That's marking point 1, but we're not going to stop there because that's just the first thing that we need to talk about. You've got sodium ions being pumped out, you've got potassium ions being pumped in, but a lot of potassium ions will then go on to diffuse out of the axon because a lot of the potassium ion channels are open. So potassium ions, once they've been pumped in, they will start to diffuse back out. So I'm going to put that as marking point 2. K plus diffuse, this is just simple diffusion now because it's going down the concentration gradient. So K plus diffuse out of axon, or you can say the membrane is more permeable to potassium ions. Now, what about the sodium ions? Now, the sodium ions got pumped out. Can they diffuse back in? Well, some of them might diffuse back in, but most of the sodium ion channels are closed, as you can see here. Most of the sodium ion channels are closed, so far less or far fewer sodium ions will diffuse back into the axon. So less sodium ions diffuse into axon. Or you could say the converse of this, which is the membrane is less permeable to sodium ions. Now, let's try and understand how this actually maintains the resting potential. Look at what's going on. You've got positively charged potassium ions going out, and that would be 3. You have got positively charged potassium ions coming in, but then they are diffusing straight back out. And the sodium ions can't get back in because their channels are closed. So the overall movement is you've got far more positive ions outside of the axon than you do inside the axon. You're going to get a build-up of sodium ions outside here. So that's why the resting potential is maintained at about minus 70 millivolts. We're basically saying that inside the axon is about 70 millivolts more negative than outside of the axon because so many positive sodium ions are outside here. If you enjoy content like this, make sure to hit the subscribe button and click the link in the description below to join my biology course.